Hello everyone, this is Dr. Lennon, and today we're going to talk about finding areas between curves. So the basic idea isn't that difficult. Really what's going to happen is we're just going to look at a bunch of examples and see what's going on. But let's say we have two curves, f of x and g of x. And, let's suppose f is going to be the curve that's on top, so f of x is greater than or equal to g of x on some interval I. So we've got this picture, maybe g of x looks like this, and maybe f of x is just something like this. So on this region, from say A to B, this is our interval. Maybe we want to figure out what this area is. And the way to do that is pretty simple. We just set up the integral almost exactly like you'd expect. So the shaded area is given by the integral from A to B of f of x minus g of x dx, because that is the function that's on top during that region. One of the things that'll be difficult sometimes is if we have two curves and they just give us two formulas. A lot of times we may have to set them equal to each other to solve for points of intersection on that interval before we can go ahead and set up our integral. But the basic idea is really straightforward in this section, and it's just going to give you more practice finding some integrals and maybe looking back at some algebra in terms of solving for the endpoints of our integral. But let me go ahead and get the first problem set up, and we'll go through, we'll do a few examples. Okay, so here's our first example. We just want to compute the shaded area. And it looks just like the one we drew when we were talking about the idea. We've got a line on top, a parabola underneath, and we want to compute the shaded area. So the first thing is we want to figure out the x values when they're equal. So basically what you do there is you just set x equal to x squared minus 2. And then go ahead and solve that. So start by subtracting x on both sides, and then this can be solved by factoring. So we end up with x minus 2 times x plus 1. So our two x values are x equals -1 or x equals 2. So those are the endpoints. Those are the points on the graph where we see the two curves intersecting. So now we can set up our integral and go ahead and figure out the area. So the area is going to be the integral from -1 to 2, and notice the graph x is on top, so we do x minus x squared minus 2 dx, and then we just compute this. So this is the integral from -1 to 2 of, if we do it in, if I rearrange the terms in order from largest power to smallest, we have minus x squared plus x and then plus 2. So this becomes minus x cubed over 3 plus x squared over 2 plus 2x from -1 to 2. And we can go ahead and just plug that into our calculator, and we get our answer of 4.5. So let's move on to another. Okay, for part B, let's go ahead and look at this example. We're trying to find the area between sine and negative cosine over that region. So again, we still want to figure out what the points are, so we have to go ahead and set that up. Say sine of x is equal to minus cosine of x, and we want to think about where that's going to happen. One way that might be easier to think about it is just dividing by cosine and then thinking about everything in terms of the tangent of x. So this problem is equivalent to thinking about when is the tangent of x equal to -1. And so if you think about on the unit circle, that's going to happen in quadrants 2 and 4, where sine and cosine have the same modulus. So it'll be here at 3 pi over 4, and down here in quadrant 4 at 7 pi over 4. So those are going to be our limits of integration, and they line up in the picture. Technically, right, there's infinitely many solutions to tangent of x equals -1, but we're just looking at those two in particular based on this graph. So basically for us it's x equals, and actually they're using the -1, so we should actually probably start there as well. So think about not 7 pi over 4, they're using negative pi over 4 here. So we're going to use x equals negative pi over 4 or x equals 3 pi over 4. Then we just do the integration. So let's see, this area here is going to be equal to the integral from negative pi over 4 to 3 pi over 4 of the sine of x minus negative cosine of x, which is really just plus cosine of x dx. So this has a pretty simple antiderivative. We've got minus cosine of x plus the sine of x from negative pi over 4 to 3 pi over 4. And then from there, we're just plugging everything into our calculator to figure out what the values are. You can get an exact value here because we know sine of x and cosine of x are all going to be some form of radical 2 over 2. And in fact, it just does come out to 2 radical 2. So basically, you just have 4 copies of radical 2 over 2. But anyway, not so bad on that one. Again, maybe the hardest part is just remembering how to solve the x values in terms of trig. But the actual integration was very easy here. So this third example gives us another way to think about things. Some curves are more easily defined in terms of y than in x. And so for that reason, you may want to integrate with respect to y. So slicing horizontally and using the y values rather than the way we typically do vertically from left to right. So this is such an example. So really what we want to do here is solve for the y values, and then we'll integrate with respect to y. So we'll be integrating from the bottom point of intersection up toward the top. So we're integrating from bottom to top here. So let's go ahead and solve for our values, which will now be y values. So we have 2y equals y squared minus 3. Again, this can be solved just by factoring, I think. So we get y squared minus 2y minus 3. So this factors into y minus 3 times y plus 1. So here y is equal to -1 or y is equal to 3. So set up our integral. So our integral, we're integrating from y equals -1 all the way up to 3. And the curve that's on top, or in fact, so I believe actually we want to think about the curve being to the right. So we're creating like horizontal slices here, but the slices are moving upward. So we're going to be taking 2y and then subtracting the y squared minus 3 curve to get our width, let's say. So we want to do 2y minus the quantity y squared minus 3, and we're integrating with respect to y this time. So this is the integral from -1 to 3 of, let's say, minus y squared plus 2y plus 3 dy. So this is minus y cubed over 3 plus y squared plus 3y from -1 to 3. And again, we can just plug in the numbers there and subtract. So in fact, this just comes out to 32 over 3. Okay, so in this one, again, both curves are kind of in terms of y, so we're going to be integrating with respect to y like we did in part C. But we're also going to want to do this one kind of in two integrals, right? Because if we think about x equals the absolute value of y, another way to think about this, we could also think about it as a piecewise function where we have x is equal to y if x is greater than 0. Actually, technically this is in terms of y, right? So it's just equal to y if y is greater than 0. And it's equal to minus y otherwise. So then we want to find those points of intersection. Again, that's not too bad. So we have 2 minus y squared equals y. That can be rewritten as 0 equals y squared plus y minus 2. So we know this factors into y plus 2 times y minus 1. The y value we're looking for up there is clearly the positive one. So we're only taking that value. So for us, I mean, y equals -2 or y equals 1. From the graph, clearly it's the positive of those two. So we know y is equal to 1. And then from the symmetry of the graphs, we know y equals -1 will be the other limit point. So yeah, actually what we want to do is we want to split this up into two integrals. One where we're using the formula x equals y, and the other where we're using the formula x equals -y. So similar computation will show that y equals -1 is what we have on the other side. So let's write that area as two pieces, the top piece and the bottom piece. So the area of the top piece, we're going to be integrating y values from 0 to 1, and that's going to be 2 minus y squared minus y. Because we're subtracting the formula on top, the absolute value function would have just formula equal to y in the piecewise formula. And then on the bottom, we're going to be integrating from -1 to 0. And we're going to be doing, again, 2 minus y squared. But here we're going to be subtracting -y. So we've written the integral using both of those two pieces. And from there, everything's easy. So again, for this one, it was all set up was most of the work. So we're going to get minus y cubed over 3 minus y squared over 2 plus 2y from 0 to 1. And then we're going to have plus this one we have minus y cubed over 3, and then we have plus y squared over 2, and then plus our 2y from -1 to 0. So we can just plug this into our calculator and figure out the answer. So in fact, this comes out to 7 over 3. I just realized too that there's also an alternative approach to this problem where we don't have to think about the absolute value of y as a piecewise function. So alternatively, instead of writing two integrals, we can recognize that the graph is symmetrical or symmetric about the x-axis. So we could have just doubled one of the two integrals, right? We could have said the area is really just 2 times the integral from 0 to 1 of 2 minus y squared minus y dy. And that approach would have been a little bit faster. But anyway, there's no shame in doing things twice, and then, you know, the more you do that, the more tricks you have in mind to remember. So for our last example, let's do one where maybe we don't have the graph shown to us, but you know, usually we can figure out what they are. So for E, let's say the region bounded by 3 curves, bounded by y equals e to the x, y equals e to the minus 2x, and x equals the natural log of 4. So what do we have here? Well, we have two exponential functions, and we have a vertical line. X equals a number is a vertical line. So let's try to figure out what that would look like. Well, we know e to the x and e to the minus 2x are both going to have an intersection point at the at their y-intercept, which if you plug in 0 for x in either function, you're going to get 1. So they're both going to intersect here. On the one hand, you have e to the x that's, you know, looking something like this, and then you have e to the negative 2x, which is exponential decay, so it's looking something like this. And then you have your vertical line, x equals the natural log of 4. So really the region we're looking at is bounded by these three curves, and it's just the shaded area right here. Sorry, it's not the world's best picture, but we have an idea of what we're doing now. So essentially what we want to do is integrate using x as the variable, going from 0 to the natural log of 4. So let's go ahead and set that up. So our area here looks like it is going to be the integral from 0 to the natural log of 4. And clearly the e to the x curve is on top, so it's going to be e to the x minus e to the minus 2x dx. And so this integral is just e to the x. So when you bring we have to divide by -2, so that's going to be plus e to the minus 2x over 2 from 0 to 4. So if we plug that in, we're going to get e to the 4th plus e to the minus 8 over 2, and then minus 1 plus 1/2. So that's our answer. We might as well approximate it. So let's see what that comes out to. Comes out to about 53.1. Okay, so that's it for region between curves. We've seen that you can slice in the x direction, you can slice in the y direction. For each of the problems, you really have to go through, think about where the curves intersect. You may have to set up an equation and solve that to find either your x values or y values that you're integrating from, and then you also want to make sure that you are setting it up so you're taking the top curve and subtracting the bottom curve. When you have multiple terms in your problems, you always want to make sure that you're using parentheses properly. Also, in example D, remember, there's a nice little trick if we ever notice the graph happens to be symmetric. Sometimes we can do half the work by just integrating one part and then multiplying by 2. So that's always something to keep in mind. Anyway, this is Dr. Lemon signing off.